Welcome back, everyone. I hope you had a wonderful lunch and very interesting and inspiring discussions. I believe everyone will soon be in this room, and we are going to start the 2-minute flash talks right now. So just like yesterday, we will have a lineup of speakers. We are going to start on the top and then go down the list. And yes, this is a very energy-loaded event because we have only 2 minutes per presenter. I tried that. Yes, please get some in.
That works.
Dame Wendy Hall, you will hear her in a moment for the keynote also. All right, 2-minute flash talks.
Unfortunately, I don't have the time for lunch and 2-minute talk and then going to lunch again. Well, I'm Yasuhara from the National Graduate Institute for Policy Studies. Now, the major in the computer science and economics, and I'm talking about the Internet of Things. And in our model, we are talking about the scenario-based economic model. It doesn't work. Scenario-based economic model approach to evaluate the impact of the Internet of Things. So this was for the working for the Science for Technology and Innovation Policy in Japan. Well, this is a model. It's kind of the old-fashioned, but it's feasible for using when I see the interaction between the industry. We divide the industry for the 93 industries, so to see the interaction by using the input-output table based on the CZA model, to see the transition from the inform ICT section to ICT industry by the kind of the platform effect. To see it has a kind of the characteristic which is to say it's compatible to using the indisplay and intangible knowledge and tangible assets to simulation from 2005 to 2050 to see the kind of the forecasting in the future when the ICT implements in our society. For that, we are using several scenarios introducing TCP/IP-based sets. We have seen some interaction in the upper sphere, and the scenario being used in the real-time sensing system, using some sensor and using some knowledge-based system. They introducing Google, Amazon like a platform, new business scheme, and production system. Well, this is a kind of the simulation result to see the interaction of it works. To see now we could see the transition from the 2050. It works, maybe it works. Yeah. Now it works, and we could see the transition from the old-fashioned industry to the newly formed ICT-based industry. We could see the transition by the transition of the intermediate output. That's okay. So this kind of the simulation result, we could see the government as investment accelerating Internet of Things, and we could see the rapid transition from the old machinery industry to the newly formed ICT, Internet, IoT industry. So this is the conclusion. Implementation process of the IoT would increase in the total volume of production GDP, while the gap in knowledge caused by the technology and employment, the transition level of demand was increased. So in that sense, the platform business in this several utilizing the cross-sectional information technology to construct a new relationship between humankind and machine. So it's only taken 5 minutes, and I couldn't tell you the latest, so please see our working paper and see our website, which is the initiative for the science and science policy in Japan. We call it SCIDEX. Thank you.
The next speaker is from the German Center for Higher Education and Science Research in Berlin, Germany.
As a doctoral candidate, I'm very pleased to give you a presentation about my research, what is happening in the new energy vehicles field. So just based on the structural information, we can know that annual output goes steadily up. Research fields are concentrated and fixed to some degree. And the scholars from the United States and China are so active in this field. However, the cooperation intensity is not very high. I don't know why. And most researches are granted by the national fundings, especially in the United States and China. We use a co-occurrence of the keywords to show you a very clear map of the changing topics. So let's go further into these topics. One, from the industry level, we can see that scholars think the development of new energy vehicles have very strong influences on business mode and industrial ecology. And we also cannot ignore any risks and uncertainties within this process. In the next 5 or 10 years, we think this field will focus on the energy saving and emission reduction, greenness and environmental protection, and smartness and easiness, safety and convenience, just range from the technology part to the consumers part. When we go into the country level, we think China will become the largest market, maybe. And the United States is still the largest one, the most mature market. And in China, the development of new energy vehicles started late, invested in March, progressed circuitously, just reflected the respect interest patterns among different enterprises and government departments. So based on this, I have 2 questions. One is how to redefine the concept of new energy vehicle, because this term is used very differently among different papers. Second one, could we really use convergent conclusions for improvements in China? As far as I know, we don't need general solutions anymore. We need solutions that are more useful and suitable based on the Chinese situation. So that's all. Thank you very much.
We have been studying the demographics of research grant awardees. As has been well documented by others before, the academic biomedical workforce is shifting towards an older population. However, we see patterns in the shifting demographics that suggested the possibility that certain properties of the grant award process itself could be conferring advantage or disadvantage to certain groups within the research community. We divided all of the awardees into 3 broad age groups. Early stage investigators in blue. The slide is not advancing. We divided all of the awardees into 3 broad age groups: early stage investigators in blue, mid-career investigators in red, and established investigators in green. Over the time frame from 1998 to 2014, the proportion of established investigators, the green curve, rose in a surprisingly linear fashion at a rate of about 1% per year. One of the factors that may be contributing to this continual increase in the effect is the effect of multiple grants on overall survival rates. Consider this scenario. Investigators who have only 1 grant and who fail to renew that award may be forced out of the academic research community because salaries are linked to grant awards. On the other hand, investigators with multiple grants who fail to renew one of their awards will simply readjust their salary to the remaining grants and will thereby remain in the system. Multiple grants, therefore, constitute a form of enhanced survival benefit. This enhanced survival benefit can be estimated by calculating the average number of grant awards per awardee in each of the age groups. There is a gradient of enhanced survival benefit that extends from the youngest investigators with the least benefit to the established investigators with the highest. These differences are statistically significant and remarkably constant over time. In summary, we believe that the enhanced survival benefit may be one of the underlying causes of the continual increases in the proportion of established investigators. Thank you very much.
Okay, so despite what the title says, what I'm really going to talk to you today about is clustering. Many of us use data from the Web of Science or from Scopus, and we need as accurate of clusters of either papers or journals as possible to do accurate analyses. Now, Dick and I were involved in generating the so-called UCSD map and UCSD classification system about a decade ago. Kati showed you a picture of that yesterday in her presentation. Is that the most accurate discipline level categorization of science available? I don't know. Well, I do know. I'll tell you that in a minute. But Dick and I have been using co-citation clusters for about a decade, even longer, to look at topic level structures in science. Are co-citation clusters the most accurate topic level categorization available? Well, no, but we'll see that in a minute. So what we did is we went and did an experiment. We wanted to compare all of these different types, ways to generate classification systems of science. So we compared 7 different journal classification systems, journals themselves, and direct citation, co-citation, bib coupling at the paper level. And we compared them using concentration indices based on papers with at least 100 references. Somebody writes a paper with 100 references. Typically, it focuses on a topic and puts that in the context of other topics at the same time. And so what we want to do is see which of these categorizations best represent the way authors are classifying their own papers. Here are the results. You'll see down at the lower left, those are our 7 journal classification systems. And you can see that those are all in the 100 to 500 cluster area. Among journal classification systems, the Science Metrics classification system gives the best results. The one that we used, the one that we developed, the UCSD, not quite as good. But at discipline level, that's not even the best. Paper-based classification systems with about 100 clusters are far more accurate than any journal-based classification system. If you want to look at the topic level, direct citation, once again, provides the best classification. You can see the curves. There's quite a bit of distance between those curves at the top and the journal classification systems at the bottom. So we don't use co-citation anymore. We don't use journal classification systems anymore. You can see the implications for yourself here. But really, isn't it about time we gave up using journal classification systems to measure things? Thank you very much.
Actually using papers and patents. Arash Bargay, like me, if I pronounce this correctly, from Virginia Tech.
Hello. Hello and good afternoon. It's a great pleasure to talk here. I am Arash Bargay from Virginia Tech, and yesterday we heard about the reproduction of scientists, a cool topic, what we are trying to do is to extend that idea using the concept of reproduction of papers in order to build a model that can capture the dynamics of different topics throughout the world as they are progressing. So the ultimate goal is to build up a model that can endogenously explain how different topics in different countries are being studied and researched and how scientists are being engaged in those. We have built a system dynamics model including different aspects such as scientific workforce, team dynamics, collaboration networks in the world. We basically have a network of different small system dynamics models, each representing a country. And we have used the case of HIV and AIDS right now in our model for our current stage of the study. Our core models are very simple. We have 4 main feedback mechanisms: reproduction of papers, the reinforcing loop, and we take into account the workforce characteristics in each topic, how scientists get engaged in those topics, and we also include how older papers in each topic affect the probability of finding new ideas in each at each stage. And just some preliminary results, our model have been able to replicate the historical data on, I'm showing 2 different topics within HIV and AIDS, topics and scientist workforce. Thanks.
Next speaker is Giorgio MIT Institute for Data Systems and Society.
Hello, everyone. This is joint work with Jeff Alstott, Bowen Yan, and Jiangxi Luo from Singapore University of Technology and Design. In this study, we analyzed data on about 4 million US patents and 3 million inventors between 1975 and 2010. And we found that the majority of patents are authored by someone who had previously invented something in a different domain. And 71% of inventors who patent more than once invent something in at least 2 different domains in their career. So this led us to think that a precise map of the space of relatedness between technologies may be very informative of inventors' movements and their performance. So we built such map by measuring how many citations you find between 2 different technology classes compared to unexpected values that comes from randomizing citation networks. So we then built a predictive model of inventors' movements where we modeled the probability that an inventor enter a class as a function of the relatedness of this class to what the inventors already knows, the popularity of the class, and inventors' personal characteristics such as age and previous productivity. As you can see, relatedness does increase the probability that an inventor enter a class, and in fact, inventors preferentially enter highly related domains. The model is very precise and can actually predict 20 years into the future while maintaining accuracy. We then model performance of these inventors in the classes that they enter, and we use a negative binomial and logistic regression models for number of patents, number of citations, citations per patents, and the probability that the patents of the inventors is a hit in these new classes. And the model tells us that it actually makes sense for inventors to enter highly related classes if what they care about is receiving a lot of citations and making a lot of patents. But if what they care about is average quality of these patents, so citations per patents, or the probability of being a hit, then they should actually enter mildly unrelated domains because there is a sort of inverted U with some bump up at the end.
Next presentation is by Victor Yakovenko, University of Maryland.
Yes, so I'm professor of physics at University of Maryland, and I apply ideas and methods of statistical physics to study economic inequality. So it's between physics and economics called econophysics sometimes. Specifically, and of course, economic inequality, income inequality is a big subject these days, discussed in presidential campaigns, etc. But what actually is distribution of income? So we downloaded what data tells us about it. We downloaded data from Bureau of Census and made this histogram. So this is annual income up to $120,000 per year, and the histogram is the data, and the solid line is a fit. It's a fit to a very simple exponential function. This is inspired by statistical physics, but doesn't matter. The point is, exponential function gives a very good fit of the data, and it's even better to see it in a log linear scale. Take logarithm of probability, then exponential function becomes linear, and you see it's a very good fit of the data. And the slope of this line is determined by average income per year. Okay, so that is up to this income 120K, but what about high income, millionaires, etc.? They're not on this sample because it's Bureau of Census, it's questionnaires. So we downloaded data from a tax agency, Internal Revenue Service, and what we found is the following. So the blue points are the data, horizontal axis is annual income, adjusted gross income. Okay, so, and the inset is in log linear scale. Linear income is linear, cumulative probability is logarithmic. Again, we see a straight line. So the lower part of the distribution is described by exponential function. However, the upper part is a straight line in log scale. That means it's a power law. So bottom line, what we observe is the whole distribution, income distribution, can be described by 2 simplest mathematical functions. Exponential, the lower part, power law in the upper part, and this would represent the 2 classes A. And so we can take an intersection point as a boundary between classes, the social classes, as extracted from the data. And read, for example, how many people in the upper class. We go here 1 to 3%. So 3% of population in the upper class, 97 in the lower class. And there's no such thing as middle class. Data tells us so, okay? So a definition of middle class is totally arbitrary. But this is for 1 year. What we can do now with data for 30 years. This is 80s, 90s, 2000s. Now income is normalized to this temperature income. And what you see, data points collapse on the same curve. So it's, it's linear and non-linear scale and etc. So point is, message here is, relative inequality within lower class doesn't change at all in 30 years. But what does happen is the share of income that goes to the upper class. That changed a lot. And basically this is shown here. So this is red curve is a fraction of income that goes to the upper class. And what we observe that this fraction goes up enormously, basically doubles during the speculative bubble in the market, during the dot-com bubble, during the housing bubble, and the most recent bubble fueled purely by Federal Reserve. It's pretty money given to the banker. And you see this in the data. This is measure of global income inequality, I mean total income inequality. And things like Gini coefficient can be perfectly fitted by this formula within just one parameter. Share of the upper class relative to the rest. Thank you.
Next speaker, Stephen Gaboro from the University of Arizona.
Hi, my name is Stefan Koborov, and I like maps. I like the art of making maps, and I like art that is made out of maps, as in this case. Many of you have networks in your data sets. I saw several in the last 10 minutes. Ben Schneiderman has networks. Kevin Boyack has networks. Kadi has networks. Giorgio had networks. Networks usually look like the picture on the top left, but we can easily make them look like the picture on the bottom left. Why make networks into maps? Because Kati and many others have shown that the general audience is intimidated by networks and doesn't know what to do with them. Whereas everybody knows what to do with a map. They know what a country is, they know what a state is, they know what a city is. Same thing as clusters, subclusters, and so on. So the picture on the very bottom left is my philosophy. Less is more. Instead of trying to teach people to do complicated things, we can make things simpler. We have a data set, we have a tool at this address, gmap.cs.arizona.edu, which will take your networks and make them into graphs, if anybody wants to try. Oh, we also showed that through experiments with human subjects that maps are better on several levels when you compare them with node link diagrams. People remember them more, they engage with the visualization more, and they do well in tasks. One way that we applied these maps was to create a map of computer science using 2.5 million papers from DBOP. And conveniently, the overall map looks like a brain. And then you can see different activities in different fields or by different scientists as little fMRI diagrams on the top right and the bottom right. So when you have a hammer, everything looks like a nail. So we can make maps of everything. Yesterday, Daniel McFarlane had a map of universities. I asked him immediately for the data so I can make a real map out of it. It will look like this. But this is a map from college admissions, and it shows how different clusters of colleges form. On the top right, you see a cluster of Ivy League schools and Ivy League wannabes. And on the bottom right, a cluster by geography, the Northwest. If anybody wants to talk about maps with me, find me.
Let's see here. Okay, so I'm actually going to practice my storytelling a little bit after the last session. So I really want to first I want to thank Ben Schneiderman for sharing my work yesterday. It makes my job a lot easier today. But I want to talk about three things related to our research. One is a discovery, two is a question, and three is a practical policy outcome. So, slide. So when we started working on the temporal analysis event flow type stuff, I had to start thinking about innovation differently. And like many of you, I've been working with networks for a long time, building innovation networks, and I've seen a lot of good ones here. But working with temporal data, we have to look at innovation as sequences of events or activities that are connected, ending up in a, with the end goal, oh, sorry, I can't go backwards, huh? Can I, there we go, point it in the right place. With the end goal of a product launch. So the end goal of innovation is the creation of a new product. So looking at the data that way, but these products are developed by people, by teams of people and networks of people. And so every event has its own little event network. And when you aggregate those, you get some really interesting things. So the discovery for me was that looking at the temporal data helped me understand the networks better. And I really was not expecting that. And so if any of you are interested in working with event flow and temporal data, it helps. The second thing to question, how long does innovation take from the time you get the idea to the time you get a product on the market? Does anybody have a statistical answer to that? I've not been able to find one. And so that's the question, one of the questions we're trying to answer with this work is, how long does innovation take? And this is has some impact. If you can figure out how long innovation takes, you can reduce the uncertainty, you reduce the risk, and you are able to get more investment into innovation earlier, and that's an important outcome. And then finally, a policy outcome. This is a network my students and I did a analysis of Howard County, Maryland last fall, and this is one of the more interesting findings, which is a regenerative medicine cluster. And when we showed this to the economic developers in Howard County, they said, this isn't even on our radar, okay? It doesn't show up in the classical cluster analysis that we do. And so we were able to show them this and then show them, give them the data behind it and show them where to target their strategies. And so I checked back with him a month later, and he said, this has changed the way we do economic development. And they're building it into their comprehensive economic development strategy going forward. So, so that's a successful policy outcome. And with that, thank you.
Next presenter is Mark Moore, Biocomplexity Institute at Virginia Tech.
All right, information diffusion on physical symbol systems. So what the hell does that mean, right? I'm not quite sure if I know, but I'm going to try to express it right now. Information diffusion, I think everybody here understands the idea. Think of social networks, think of ideas spreading, culture, or procedures. Physical symbol systems, what is that? In this context today, a physical symbol system is really about humans. It's from psychology and AI. Think Herb Simon, Alan Newell. But it doesn't have to be humans. It can be computational systems that actually help you model physical symbol systems. But right now, what I'm going to talk about is understanding the relation between these two types of systems and then the implications it has for how we might model innovation. So the production of novelty in physical symbol systems. This is from a colleague of mine, Stellan Olsen, a book in 2010, Deep Learning, How the Mind Overrides Experience, from Cambridge University Press. The idea here is, think this is really about people and how people produce novelty. It implicates process, and it does not think about comparison of outputs and products and widgets as more or less innovative. It doesn't think of individuals of having characteristics. Person A is more innovative than person B. It's about a process on a physical symbol system. It's a very specific way that novelty is created. It raises questions like, what is novelty? How is it possible? Why does it exist? Think of this. Is necessity the mother of invention? Think of artists and scientists. I would argue that that's not really true in most cases. Now, here we have this network graph here is a collection of physical symbol systems. It has 250 computational agents. These agents could be teams, firms, individuals. On the right, you see thousands of simulations of a diffusion process of innovation. And you see two different states, which is a state of the network, which is a state of how innovation is actually diffused. The difference here between the two phases is actually a function of the physical symbol system and not network topology. That is to say, the psychology in this case changes how innovation diffuses on a network. This is the final point. This is the foresight map. Has anybody seen this? This is about obesity. It's about obesity. In the middle is actually people and how people operate in physical, social, economic, and political contexts. It's a large system itself. This is a way to think about innovation. This is a parallel. If you put physical symbol systems in the production of novelty in contexts like social, economic, and political contexts, that's a way we can think about modeling innovation. Thank you.
Next presentation is Julie.
Thanks. Hi, everyone. I'm Julia Lauren. I'm head of product development at Thomson Reuters for our academic solutions, which means Web of Science, EndNote, Insights, Converis, and ScholarOne, for example. And what that means is it's my mission to essentially solve pain points for researchers and for other stakeholders in the research ecosystem. And I'm especially excited by the power of models to help us with recent recommendations projects. So the focus here is really for how can we use models to present some non-obvious options to researchers in their workflow. I'm going to walk through very quickly 3 projects that we've done that all have a couple things in common. One is they use WAS data, and they also apply big data technologies, so we can do this at scale. The second is that they're embedded in and use the workflow of the researcher, for example, workflow, EndNote, ScholarOne. And finally, they're helping to make decisions, again, by presenting more of these non-obvious choices. So for example, in ScholarOne manuscripts, what we were looking to solve was the issue of peer reviewer fatigue, of hitting the same population of researchers over and over again to ask them to peer review a journal. And this was a big, a manuscript. And this was a big problem for editors who are constantly looking for a fresh population of reviewers. So by creating a fingerprint of the article, of the publication, and applying that against WAS data, we were able to present some new choices for reviewers for journal editors. The other side of the coin here on EndNote online, this is on EndNote Web, is a manuscript matcher for helping to answer the question of where should I be submitting my draft publication for a journal, right? So this is a big question as well, and a very important question for a researcher and their career. So we, again, apply the same concept of a fingerprint of the manuscript, the cited references in that manuscript, and the EndNote library, and apply that to WAS data to suggest and recommend other journals. And what I really like about this approach is that we also have a thumbs up, thumbs down in the model itself on EndNote Web Online. So this is freely available for anyone to use. You provide feedback to us that we in turn use to fine-tune the model. Finally, a current project under kind of in the R&D phase is EIGENFACTOR recommendations for Web of Science articles. And this is a collaboration with the University of Washington, Data Lab, and in fact, Carl Bergstrom is here as well, so you can direct all of your eigenvector questions to him. But what we are doing here is essentially looking to answer that question we talked about a lot this morning, which is what to do with this burden of knowledge. How do I find what I need to read if there's a new article in the Web of Science every 20 minutes? So we have here done something novel to apply eigenfactor network approach to the article level and not just to the journal level. This allows us to create a very rich graph of recommendations that take into account metadata in Web of Science, that take into account the centrality of certain articles, and that in turn lets us answer 2 types of questions. One is classic recommendations, so to identify clusters of articles that are essential to a certain field if you're looking to learn a new discipline, as well as expert recommendations if you're looking for kind of more hot and highly cited types of papers in that discipline. So if any of this is interesting to you, we actually are in kind of alpha testing mode, so come find me and I'd love to get your feedback on our project. Thank you.
Where do I have to click?
Hi everyone, I'm Andreas Buckler. I'm a PhD student at Indiana University, and I also have a side career as a photographer, in case this whole academia thing doesn't work out for me. If you remember, yesterday Caddy showed this little 2-minute clip of our science forecast pilot. And I want to tell you a little bit about the production history of this thing. Our goal is to bring science forecast maps to people and make it more appealing to a broader audience without necessarily dumbing down, of course. And what we did is we used an established medium as a template. In our case, weather forecasts. I really, really like the picture on the left. It's like 60 years old, but I still like it. It's amazing. Because we thought that forecasting science is very similar to forecasting weather in a lot of ways. For example, the weather was always regarded as sent from the gods and unpredictable. It was almost a sin to try to predict it. Until in about the 18th century, people started to collect data and actually organize themselves like over a wide array of geolocations. And so this is pretty much what we want to do too. We want to forecast science in a way that weather is forecast today. And we hope that at some point in the future, we can create science forecast maps that are easily understandable and readable for everybody. Thank you.
Thank you all for going up for the challenge of a 2-minute talk. I think you did marvelously. And just like yesterday, you should get a second round of applause.